This lecture is on distributed generation. Please do the readings before watching this video. They will provide context and help you understand the topics we're going to talk about. So the agenda is distributed generation and net metering, Lucas Davis's blog post, and the Duct Curve. Small-scale electricity generation at homes and businesses is called distributed generation. Or distributed generation. There's a variety of technologies that generate electricity at or near where it will be used. So distributed generation technologies, we have solar photovoltaic panels, small wind turbines, emergency backup generators, usually fueled by gasoline or diesel fuel. So it's essentially generators that are not utility scale. They exist at homes or on farms or something like that. In practice, distributed generation means rooftop solar. As you can see on this house, you've likely seen this on many houses at this point. This is one example of distributed generation. Where is residential solar? States with the most solar PV typically have high electricity prices. There's an incentive for you to put solar on your house if you're paying a lot for electricity. They have strong solar resources like subsidies and state incentives. So this little figure on the right shows the amount of distributed solar in megawatts by the top performing states. So California clearly wins here. New Jersey, Arizona next up, and Massachusetts, you can see sort of the distribution. Most places use net metering to compensate customers for their solar PV generation. What is net metering? Why would you put a solar panel on your house? Well, you put the solar panel on your house because, one, you don't want to pay the utility for electricity anymore. Two, because you think it's going to reduce greenhouse gas emissions. And three, because maybe you can sell some of the solar energy you produce back to the utility. And that's what net metering refers to. Net metering allows electricity to flow both to and from the customer. When a customer's generation exceeds her use, the electricity flows back into the grid, offsetting electricity consumption at a different time during the same billing cycle. This excess generation offsets electricity that would otherwise be purchased at the utility's full retail rate. So the key here is that when you have a solar panel on your house and you have excess electricity and you send some of that electricity back to the grid, you're receiving the retail rate of electricity oftentimes for your electricity production. Is it fair for a household to receive the retail rate of electricity, whereas a utility scale generator receives only the wholesale rate of electricity, which is lower? California is an interesting case study because California has the most solar. They've had the most aggressive policies. It will be interesting to see if California sticks with net metering. We'll see why it's causing problems in a moment with the Duct Curve. California has a reputation for environmentally friendly policies, but the problem is that there's big shifts in the cost from those with solar PV to those without, and that's what Lucas Davis's article is talking about. Lots of households with solar PV and increasing block pricing means that the households without solar are paying more of the fixed costs of the generators in the state. Another issue is that utility scale solar, so this is solar bought by the utility and produced on site where the natural gas plant or the coal plants are, or maybe not necessarily next to them, but utilities buying solar in bulk essentially, and it's much cheaper than rooftop solar or residential solar. In the U.S., the U.S. is simultaneously building two types of solar. We have utility scale or grid scale, typically greater than 1 megawatt, and residential rooftop solar, which is typically 2 to 5 kilowatts in capacity. So the utility is much larger, and so we have, again, economies of scale. What number do we usually use to compare various types of electricity generation? We use the unsubsidized levelized cost of energy. That's the LCOE here. In 2017, we've seen the Lazard levelized cost of energy before, but the 2017 estimates, utility scale solar was $43 to $53 per megawatt hour. This is the cost of production. Residential rooftop solar was $187 to $319 per megawatt hour. So it's much better for the utility to invest in solar than it is for individual households. One alternative to this is utilities could rent rooftops. If you were short on land, you could rent rooftops in neighborhoods, and the utility could pay to put solar panels on top of rooftops. Utility scale solar produces more per kilowatt of capacity, so they're more efficient. This is what this graph is showing. So this graph shows solar PV average monthly generation for all utility scale in the light gray, that's the highest, and the distributed small scale is the dark gray or blue there. Rooftop solar does have some advantages though. There's lower distribution costs, right? Because if you have the solar panel on your home, then you don't have to build a transmission line. There's increased grid resiliency through spatial diversification, but they don't make up, these advantages don't make up for the higher costs. Another issue is that it can be problematic that solar is intermittent. We've talked about this a little bit, but let's dive into this a little more. It's great that solar generation is high in the afternoon. Why? Because that's when the peak demand is. But what about when the sun goes down or it gets cloudy? Then solar generation dramatically drops off. Dramatically at night, it drops to zero. Demand is still high, so other generators must quickly turn on when solar stops generating. This increases ramping costs for conventional generators. So this leads us to the duct curve. The duct curve is showing, this one in particular is the California system. This shows the net load, net of solar PV provision over time. And so you can see the gray line is 2012, when there was very little solar PV in California. And it gives you kind of the daily load profile for California. Each of the subsequent lines are the net loads year after year. So net load being the amount of demand minus the supply from solar electricity generation. And as more solar panels have come online in California, that net load is declining, right? Because there's more solar providing electricity, particularly during the sunny hours of the day. And that's why you can see the belly of this duck kind of dipping down over time. The real issue here is that going from about maybe 4 p.m. to 7 p.m., we need a ramp up of 13,000 megawatts in capacity. That's a huge increase in the demand on fossil fuel generators over a short period, which means they have to ramp up their machines really quickly, which adds wear and tear. And so there's in some places they're starting to essentially tax intermittent generators in order to cover the ramp-up costs of the non-intermittent generators that have to meet the residual demand when solar goes offline. So where do we go from here? How do we fix this problem? Well, one obvious solution is going to be battery storage. If we can store electricity, we don't have this ramp-up problem. We store electricity from solar during when there's excess solar during the day, and we use it to cover those that ramp-up period when the sun is going down. And real-time pricing. If customers see that the prices are spiking, they're going to curb their electricity use, and that's going to add some elasticity to the demand curve, causing customers to not use as much, and it'll soften the blow on wholesale electricity prices and the need for ramp up.